Right.
All right, so what we're going to do now is before we go on to chapter 4, earlier today we finished chapter 3 with our introduction to antiderivatives. So now what we're going to do is work on some problems just to get some more practice with the concepts that we covered in chapter 3 before diving into chapter 4, which is a fairly complicated chapter, but it's again awfully important. And so here we'll get an opportunity to do a few more of these types of problems, which hopefully will be similar to the ones that you do in your assignments. So also at some point we have to start thinking about an exam, and questions like this will be on there. The type that I'm about to show you, that is. So let's begin at the beginning. Here's our chapter 3 problem set, which by the way, I only just posted this very recently. You might not have noticed it there. But it suddenly dawned on me that as we're getting towards the end of chapter 3, it would be nice to have some more practice problems. So I put these together. And so let's go over these right now. So first, we're going to look for critical points. And so don't forget what that means. A critical point is one where one of two things is true. Either f prime of c is 0 or f prime of c is undefined. Okay, there's one thing though that I just want to mention here. A critical point must be in the domain of the function. In other words, it doesn't count if, I mean, these rules are true, but only if the point that we find is in the actual domain of the function. If not, then it doesn't count as a critical point. So we're only focusing our attention on points where within the domain of that function, either the first derivative of that at that point is 0, or else it's undefined. All right, now for a polynomial like this one, that shouldn't be a problem. So what we're going to do is take the first derivative of this function and set it equal to 0 and solve for x. Now, of course, because we're taking the derivative of a cubic function, the result will be a quadratic function, which should have two solutions. And so using the power rule, we have 12x squared minus 3. We set that equal to 0. And then when we solve for that, as we predicted, there's two solutions because we're taking the square root, which can lead us with a positive or a negative result. And of course, the square root of 1/4 is simply 1/2. So those are the two critical points that we're looking for. And while we're at it, why don't we go ahead and go into Symbolab and take a look at what this graph looks like so we can see where they would be located. And so we'll have, let's see, the function is 4x cubed minus 3x. And it is a cubic function. And this is what it looks like. So you can see here, this is one of the two critical points, -1/2. This is the other one, +1/2. Now, the problem doesn't ask us to determine if these are relative maxima or minima. It just wants to know where the critical points are. So we're actually done with this problem right now. Later on, though, we will be asked to find whether the points are minima or maxima. Now, here's a scary looking one, because if you notice, we're going to have a discontinuity in the function. And I know we've seen this one before. 1 over x minus 1, or something similar to this. And so let's remind ourselves what this looks like. Oh yeah, this one. So you can see there's a vertical asymptote at x equals 1. The function will never quite reach a positive 1. And so that would be our vertical asymptote. And that means that x equals 1 is not part of the domain. Okay, let's keep that in mind. The domain is everything except 1. So we'll write that in our interval notation. And that means, remember the way we write this, the fact that this is a round bracket or a parenthesis means that 1 is not included in that interval. So another option would be to do something like this. Symbolab sometimes writes it like this, just x not equal to 1. And you know, you get the idea. Anyway, so we're going to go ahead and take the first derivative. Before we do that, though, let's rewrite it slightly. I think it's easier to solve for this since we're using the power rule as x minus 1 to the minus 1 power. So you can see that if we're using the power rule, we need to identify the k and the n. Actually, let me rewrite this as f of x. And therefore, f prime of x is n k x to the n minus 1. And so here, there's an implicit 1 here, that's our k, and n is negative 1. So the derivative, based on the power rule, is negative 1 times positive 1 times x to the minus 1 minus 1. And we end up with minus 1 x to the minus 2, or negative 1 over x squared. Okay, so now here's the problem. We're going to try to set that equal to 0. Well, it turns out there is no value of x that could cause this ratio to equal 0. So here, the result is that there is no critical point. Okay, so yeah, it's not possible to find a value of x that would cause this ratio to equal to 0. So therefore, there simply is no critical point. And you can tell by looking at it. I mean, there is nowhere along this curve where the slope is exactly equal to 0. Okay, so there isn't going to be a critical point. Okay, now let's try another one. About this one. Now here it says to find the local extremis. So in other words, when we get to the critical points, we're going to also identify whether they are local or global maxima or minima. Okay, so first things first. And by the way, this is a polynomial. There are no discontinuities. It is defined over the entire interval negative to positive infinity. And we'll confirm that by looking at the graph. Oh, sorry, it's y, what am I doing here? Y equals x cubed minus 12x. All right, let's see what this thing looks like. All right, well, it's a little strange, but it is a cubic function, and you can see there's no discontinuities or any sharp breaks. So the interval and the domain is, of course, the entire real number line. So any critical points we find will be the ones we need. And so first things first, let's find the first derivative. Of course, we'll be using the power rule on each term. Set it equal to 0 and solve. All right, so x squared equals 4, which means that x equals plus or minus radical 4 or plus or minus 2. So we have two critical points, plus or minus 2. And you can kind of see, yeah, it's a little tight here, but actually let me. I guess that helps a little, I don't know. But so you can see, yes, it agrees with us. -2 is here, +2 is here. And now they're telling us that we have a minimum and a maximum, but we need to figure it out ourselves. So we can apply the first derivative test. And so for the first one, which by the way, if you need to know the y coordinate at this point, all you have to do is take the x value and plug it into the original function. And so for this one, you'll end up with -216. And so what we're going to do is test the sign of the first derivative on either side of that point. Okay, so let's start with 1. Sorry, -3 will be good. Because it's just to the left of this point. So remember the derivative is actually let me just copy this in here again, just so I don't have to keep scrolling back and forth a million times. And so to evaluate f prime of -3, we'll have oh yeah, no, that's right. Sorry. Fix that. It's 3 times +9 minus 12. 15, which is positive. Now you can see that from this graph. The slope is positive. The tangent line has a positive slope just to the left of -2. Now we'll try the same thing on the right-hand side of this function. Let's try -1. So that one is negative. And so this set of results tells us, because we're going from f prime of x goes from positive to 0 to negative, that implies that this point is a relative maximum. So now we're going to do the same thing for the point +2. And again, if you plug 2 into this equation, you'll get the y coordinate, which turns out to be -16. That'll be over here somewhere. All right, so let's do the same thing. We'll take the first derivative and evaluate it just to the left and just to the right of that point, and let's look at the signs. So first, a quick reminder, the first derivative is 3x squared minus 12. Let's look at 1. That 1 is slightly to the left of 2. It's negative. Okay, and then let's try 3. That one's positive. Okay, great. So since f prime of x goes from negative to 0 to positive, that means that this must be a relative minimum. All right. So that's all there was to that. Now, I mean, we could have done it a different way, but this is just as easy. So now here we do have to watch it because we are going to be asked to do a lot. We're going to be looking at intervals where the function is increasing and decreasing. We want to know where are the local maxima and minima, intervals where we have concave up, concave down. and inflection points, if any. All right, so let's take a look at this one. X squared minus 6x. All right, well, from the graph, you can see there's going to be a single relative, and which actually happens to also be the absolute minimum right here. So, but we also want to understand what's going on around this point. So first, we'll take the first derivative. And then the second derivative. Okay, now you can see why the function behaves this way. Second derivative is always positive. It's a constant. It can't be anything else. So that means the entire function is concave up. And that's why that relative minimum is also a global minimum. Okay, there cannot be any other points where the function gets smaller than that. But let's try this. Let's go through all the steps anyway, and we'll say, all right, well, where is the relative maximum or minimum? All right, so that's 3. And you can solve for the value of y by plugging this into the original equation, which was x squared minus 6x. And so f of 3 is 3 squared minus 6 times 3, 9 minus 18. All right, now we can check the intervals where it's increasing and decreasing. We can just simply look at the first derivative on either side. Now, it's already clear that there's only a single critical point. So we really only have to test what's going on to the left and to the right of that critical point. There won't be any other intervals where something different is going on. So let's do this. Let's confirm what we think we know by looking at this graph by trying f prime of 2 rather. Okay. So since f prime of x is 2x minus 6, we'll have 2 times 2 minus 6. Okay, and so as we would have expected, the slope is, the tangent line is negative. And then let's try 4. And that's positive. All right, so we know that the function is increasing and decreasing. All right, let's start keeping track of this. It's actually increasing from negative. Well, actually, it's coming from positive infinity. So infinity to 3 and decreasing from 3 to infinity. Okay, or if you want to use the interval notation. Let's try that again. Let's go. So it's initially in decrease, sorry, it's decreasing initially as we go from left to right. The function is decreasing from infinity to 3. Actually, in this case, instead of saying decreasing from, I'll say decreasing over this interval and then increasing over 3 to infinity. Okay, and we already know that the relative minimum is this point. What else do they want to know? Now, as far as concavity goes, let's take the second derivative. Actually, we did that a little bit earlier, and we discovered that the second derivative is a constant. So we already know how this works. Second derivative is and so what this indicates is that the function is concave up over the entire domain and has no inflection points. Because that would imply that the sign of the second derivative is changing somewhere, but we can see clearly that it is not. Okay, so this one was pretty straightforward. I mean, it's basically a parabola that's facing up. And so it's pretty straightforward. The next one is a little bit trickier.